Hello, my name is Luke John P. Barameda, and we're going to discuss about rational functions, equations, and inequalities. Now, it might sound scary, but by the end of this lesson, it'll be much more easier to understand. Today, we're demystifying rational functions. Think of them as just fancy fractions that open up a new world of math. By the end of this lesson, you'll be solving these problems with confidence. Let's conquer them together. Here's what we'll unpack today. We're going to discuss on what are rational functions, solving rational equations, working with rational inequalities, and step-by-step examples. You already know fractions. Rational functions are just a natural extension of what you've learned. In this slide, we can see that rational function is just a polynomial fraction, with px and qx being the polynomials and qx never equal to zero. Now you may notice that every rational function has the variable f of x, or any letter. Just like regular fractions, the denominator of a rational function can't be zero. This is crucial for defining its domain. Let's look at some examples. In example 1, a linear polynomial over another linear polynomial if f of x is equal to x plus 1 over x minus 2. In example 2, we have g of x is equal to x squared plus 3x plus 2 over x squared minus 4, a quadratic polynomial over another quadratic polynomial. In example 3, we have h of x is equal to 5 over x plus 3. Notice how the numerator and the denominator can be different types of polynomials. Now, when working with rational functions, we must find the domain. The domain of a function is the set of all possible x values we can safely use as an input. The key rule is to never divide by zero. For rational functions, the denominator can never be equal to zero. Any x value that makes the denominator zero must be excluded from the domain. In this example, we must find the domain. We have f of x is equal to x plus 2, x squared minus 9. In step 1, you may notice that the numerator is not included, because in finding the domain, we only focus on the denominator. To find the x values that makes the denominator 0, we set the denominator equal to 0 and solve for x. We factor x squared minus 9 and turn it into x plus 3 times x minus 3. Now, x plus 3 becomes negative 3 and negative 3 becomes positive 3. This means that when x equals 3 or x equals negative 3, the denominator becomes 0, which is undefined. In step 2, we define the domain. The domain of the function includes all real number except those values of x that makes the denominator 0. Therefore, the domain is all real numbers except 3 and negative 3. Now, when evaluating the function, in step 1, we substitute the value. Replace x with 2 in the function's expression. In step 2, we simplify the expression, turning 2 times 2 becoming 4, minus 1 is equal to 3. 3 plus 2 becomes 5, which then equals to 5. Now the answer is f of 2 is equal to 3 over 5. What is a rational equation? A rational equation is setting a rational function equal to something. It's like asking, when does this polynomial fraction equal a specific value or another expression? This something can be a number, a variable, or even another rational expression. Here are some examples. Here, a rational function is set equal to a constant. In this case, one rational function is set equal to another. Our goal will be to find the values of x that makes these statements true. Now, the secret strategy is to get rid of fractions. To solve rational equations, the simplest approach is to eliminate the denominators. You do this by multiplying both sides of the equation by LCD of all the fractions involved. Let's solve our first example. X plus 3 over x minus 1 is equal to 2. In step 1, we multiply the denominator. We multiply both sides by x minus 1, which is the denominator, to clear the fraction. X minus 1 cancels out x minus 1, leaving only x minus 1 to x plus 3 equals 2. The x minus 1 terms cancels on the left, leaving us with a simpler equation. X plus 3 is equal to 2 times the quantity of x minus 1. Next, we distribute and simplify. Apply the distributive property to remove parentheses. We, we multiply 2 to x minus 1, which becomes 2x minus 2. In step 3, we solve for x. Gather like terms to isolate x on one side of the equation. X plus 3 is equal to 2x minus 2. We exchange negative 2 with x, which becomes 2x minus x. And we move negative 2 to this side, becoming 3 plus 2. Simplify it and we have 5 equals x. And there you have it. The solution to our first rational equation is x equals 5. We're finished, but in step 4, we always check your work. This step is crucial, especially with rational equations, to ensure our solution doesn't make the denominator 0 or lead to an extraneous solution. We substitute our found value of x equals 5 back into the rational equation. And we have x equals to 2. Since 2 is equal to 2, our solution is correct. Now, what is a rational inequality? Just like rational equations, rational inequalities involve a fraction with polynomials. The key difference is that they use inequality symbols instead of an equal sign. These symbols dictate a range of possible solutions, not just a single value. In example 1, we have x plus 1 over x minus 2 is greater than 0. In example 2, we have 2x minus 3 over x plus 1 less than or equal to 5. In solving rational inequalities, the strategy is to find critical points, plot on number line, and test each interval. Let's solve our next example. X minus 2 over x plus 1 is greater than 0. In step 1, we identify the critical points. From the numerator, we set the numerator equal to 0 to find its roots, which becomes x equal to. From the denominator, we set the denominator equal to 0 to find its undefined point, which then turns into x equals to negative 1. Remember, the expression is undefined here, so this point is never part of the solution set. Now let's mark this point. In step 2, we test intervals on the number line. In interval 1, we have x is less than negative 1. Our test value is x equals negative 2. We substitute it into x minus 2 over x plus 1, which is the result is positive 4, which satisfies the equation. In interval 2, x is greater than negative 1 and less than 2. Our test value is equal to 0. We substitute it into the solution and we have negative 2, which does not satisfy the equation. And in interval 3, we have x is greater than 2. We pick our test value, which is 3. We substitute it and we have 1 over 4, which is positive. Based on our test, the intervals were x minus 2 over x plus 1 greater than 0 are when the expression is positive. So the answer is x is less than -1 or x is greater than 2. You can screenshot the key takeaways and practice tips. Congratulations, you've mastered these fundamental concepts. Thanks for watching.